Hello and welcome to our webinar on anti-product piracy. I am very glad that we have Tim Blazytko from emproof with us, and we will give you very interesting content about product piracy, about reverse engineering, about regulations and countermeasures. Tim, he's the chief scientist of emproof and also co-founder and head of engineering. He will dive us into the world of reverse engineering and we'll do some demonstrations on that as well. And after that, I will explain some things about the upcoming EU regulations as well as countermeasures that we can do inside of the physical flash chips to protect your data and your IP in there. And now I'm very happy to hand over to Tim. And I hope that everything works. By the way, this is a after recorded session. So we had this webinar already. So we are a little bit better than the first time now. But the reason was that we had some technical difficulties. So actually the Q&A session will be a little bit shorter and Tim and me will ask each other some questions. But still the content stays the same and the webinar will be in the range of 45 minutes. And now, Tim?
Yeah, thank you, Roland. Let me start my screen sharing. All right, can you see my screen now?
Yes, I can see it.
Perfect. So today I would like to talk about anti-piracy, especially what are common attacks on the firmware level, then how to protect against how does piracy work, and then what are common defenses that you can apply. So if we take a look at the attack vectors of piracy, we'll see something like product piracy, where we have this case study from VDMA. So it's a study basically from Industrial Security and Product Piracy 2024, which basically tells us that product piracy and cyber attacks are a huge threat to the industry. So product piracy, what we typically understand from that is the stealing or the theft of intellectual property, often by competitors, that we are getting analyzed by competitors, that they resell our products with our own algorithms. So basically they analyze how our inner systems work, how the algorithms work that we researched, or that they do just one-to-one product clones where they dump the firmware and put it onto another device, fix some IP addresses in the cloud backends and stuff like that, and then ship it on their own cheap hardware. This is something that we commonly see, so like product piracy. But another thing is also piracy or manipulations by the end users. For instance, to bypass license checks, to get access to premium features, by modifying the software, get access to features that you should normally pay for. But if you patch specific parts in the software or find ways to circumvent specific checks, then you can unlock them for free. Or another thing, which is quite common, is the removing of restrictions, for instance, speed limits for safety cases, or region-specific features that are only available in specific parts of the world, when then customers go and patch the firmware in a way that they still have access to other features that they shouldn't have. So these are two attack vectors that we commonly see by users. So the question is, how does this overall, how do attacks like this work? So typically we start with the hardware itself, with the system, like a piece of metal, a sensor, or something like that, we analyze the hardware. And if we analyze the hardware, our goal is to somehow extract the software. Once we have the software, we can then start typical software reverse engineering tools that allow us to dive deep into the code, to understand the binary code, to analyze how it works, and then modify it or look for bugs or something similar. So, for instance, on the hardware analysis, we often said the goal is to read out the software. Often we start with something like that, a microcontroller, where we might have some debug pins, where we might have to solder onto some connections, a serial interface or something like that to dump out the firmware. And once we have dumped out the firmware, we can proceed with software reverse engineering. Software reverse engineering is something which you usually think is quite difficult to do. However, as you will see in some minutes, this isn't really true. There is the entry barrier for this significantly decreased in the last years, and now we'll take a look how it can be done. So, software reverse engineering. The goal of software reverse engineering is to understand what a given piece of software, of firmware, does. So we start with just a binary blob consisting of zeros and ones. And this contains, for instance, code. And we want to analyze the code maybe with the goal to detect if it does something malicious. Like, is this some kind of malicious software? Or does this software contain some bugs? Or in our case, how do specific things work in the binary, in the firmware, such that I can recreate them or patch them to mitigate some checks? So basically, one common attack vector or motivation vector for reverse engineering is piracy and cracking. So initially, the reverse engineer starts with a sequence of bytes. This sequence of bytes is basically encodes instructions for the CPU architecture, which are then just executed. So basically this one encodes code. We can think about it, and there is a specific definition how the underlying CPU architecture has to decode them. For instance, it might understand the first byte of the instruction as operation, if it's an addition or multiplication. And then the next field might be the register, so the variable which is used as part of the computation, the operands. And then we might have the constants. And so we basically are able to go from something which is called machine code, this sequence of bytes, to something which is a human readable form of machine code, which is called assembly. And there is a tool which is known as disassembler, which automatically transforms or decodes machine code into human readable disassembly. Afterward, we can take a tool which is known as decompiler. A decompiler takes disassembly as input and reconstructs high-level code, like for instance C code. And being able to analyze a C code-like language, which based on the binary firmware as input, we are able to understand quite a lot. Also, we might not be professional reverse engineers. So basically, if you think that the entry barrier for reverse engineering is quite high, this is not really the case anymore. There are open source tools like Ghidra, which is a very powerful open source reverse engineering framework, which allows you and everybody else to download it from the internet and then to load in your binary. And based on that, you can automatically see the disassembly and the decompiled code. Of course, a professional reverse engineer can be more powerful in terms of attacks than a beginner reverse engineer. Like a senior can have a good understanding about the disassembled code and can navigate more into that. However, to get a baseline understanding for a beginner, the decompiled code is often sufficient enough such that the attacker can perform a lot of analysis without having deep knowledge about assembly code. And now I would like to form a small demonstration. So here I'm on the website of Ghidra, where I could just download it, but I prepared it somewhere else. And then I switch to a terminal. And in this terminal, I have a file, this cardemo.elf. And this is basically the file that we dumped from a piece of hardware. If we take a look with the file command at that, we can see that this is a ELF 32-bit executable for the ARM architecture. And now we can run Ghidra to analyze the file. Here we then double click on that, and in some seconds we will see something that allows us to analyze the binary. So for instance, in the middle we see some code. It's still analyzing. So we see some code. And this one basically in the middle here is assembly code, where we see this is a function main, which has some assembly code. However, let's not look at the assembly code. Let's look at the right-hand side. Here, where we see main. And here we see that we call another function called hull entry. If we double click on that, we see then that we jump into another function, Arduino main. And if we take a look at that, we see the real main function with some high-level logic. We see that we have some loops here, that we operate with some strings, and that we basically call the logic. So we are able to see the entire logic of the code without, and are able to understand this quite well because we can analyze its high-level code. For instance, I could also go to a function like count pulse, which implements some custom logic. And if I take a look at that, I can even see that I have my function here. I can see its parameters, its variable names. I can see that I have a loop here, that we check something, that we have another loop here. So I can see quite a lot from the original logic by putting the binary into Ghidra and just analyzing its code. I could do even more. For instance here, let's check this check for unequal here. If I would like to edit this, because let's say this is a serial license validation or something like that, what I could do is I could go and say, for instance, patch instruction, and then it initializes the assembler, and then after some time it's possible for me to modify this instruction. So instead of jump equal, I could modify to jump not equal, for instance. And if I do that, I see that this unequal sign has been switched to an equal sign. So now what I could do, for instance, I could just save it as a new binary and then have the modified binary and could flash this back onto the device, and then I would have bypassed the license check, for instance. So jumping back to the slides, we can see that reverse engineering is quite doable with something as Ghidra. So the question is there anything we can do to prevent that from a technical point of view? And the answer there is yes. There's a technique called software hardening. And there are two things we can do. One of them is code obfuscation and data encoding. For instance, with code obfuscation, the idea is to add specific layers of complexity above the code, such that the code at all looks more complicated. So we basically increase the time effort of a reverse engineer by finding and understanding the right code parts in a mess of code mazes and different layers. And another thing we commonly see is hard-coded credentials of username and passwords, or of hard-coded cryptographic keys for AES or for RSA and so on. And these are often stored in plain text in the binary. Another thing you can do is something which is called data encoding, which basically ensures that the data, that the keys and the passwords in the binary are not stored in plain text, but somehow encoded, such that if you run the binary, if you run the firmware, they are just decoded at runtime. So this basically allows you to hide keys and credentials and also the underlying code logic from the attacker who loads the binary into Ghidra. So these are basically passive protections to impede reverse engineering. There are also something which is called active preventions of reverse engineering, something like anti-debug and anti-tamper. The idea behind anti-debug, for instance, is to pinpoint the environment to check if some debugger has been attached. Because if a debugger attaches, the environment changes in specific ways. And so we could write a detection to detect debuggers. And if we recognize that a bugger is detected, that a debugger is active, we, for instance, could terminate or go to an error state, which allows us to basically to prevent the analysis of the original code. Another thing to prevent patching or cracking, what I demonstrated before, where I rewrite some code parts to circumvent some checks, is the idea there's a technique called anti-tamper. The idea behind anti-tamper is to introduce code checksumming. So we compute a cryptographic checksum about code and compare it against a hard-coded value. And if somebody should change the code, the checksum computation wouldn't match up anymore. And therefore, we detected that somebody modified valid code or memory regions. And so therefore, we can terminate. And with these things, additionally applied to obfuscation, like anti-debug and anti-tamper, we also have runtime protections which prevent analysis and modifications. And there's something, so let's go back to our original demo here and open another binary, this time the protected one. So the protected one is exactly the same binary as before, with the difference that it's being obfuscated. For instance here, if we jump to the main function, if we see the main function, where we see all this logic, this is this here in the original binary. If we jump to the same location in the modified binary, we see first, we don't have function names anymore. And then we see that we see some logic, but then Ghidra tells us there's a bad instruction. It just doesn't know what to do. Also on the assembly side, it doesn't recognize code anymore here. So it just doesn't know where to go and what to do. So the reverse engineer doesn't see any of the code now. Let's go to the other function, count pulls. Here, where we were able to see the entire control flow and the logic. If we now go to the same address in the protected binary, we again see something pretty similar. It just doesn't know where to go or how to decode it. It doesn't make any sense. So basically, we don't see any more the original code. And what we see is just garbage. So this is one technique of many possibilities to prevent or to impede reverse engineering. A professional reverse engineer, of course, could bypass that, given enough time and money. However, it would take a significant effort to understand how it's going on, to know how to fix this in the tool, to know how to analyze the code in a deep manner, to rewrite it, and so on. So it requires now a large time effort and also knowledge effort for professional reverse engineer to go on with the analysis, to go on with the cracking. So it's still possible with enough time and money, but the challenge for that is significantly higher. Especially beginner reverse engineers who can do quite a lot of powerful things with Ghidra on unobfuscated binaries can't do really much on obfuscated ones. So there, the challenge is significantly higher. So to conclude, the attacker motivation is often piracy, from the end user or competitor analysis or modifying the firmware. Typical attacks there are first hardware-based analysis to dump the firmware and then to reverse engineer the software. And then on the software level, what you can do to harden it is code obfuscation, anti-debug, and anti-tamper. And now I would like to go back and give the word to Roland.
Thank you, Tim. 1 second. So I hope you can again see my screen.
Yes, perfect.
Okay. So yeah, so I was wondering, okay, how can I go from reverse engineering to my topics? And actually one way how you can like combine these things is anti-piracy methods or anti-reverse engineering methods are to protect your product. So it's actually security. And for many products, this is already done. Valuable products, for example, but not for all products. So if you have a smart home, very cheap devices, they are not well protected normally. And also there are some open source things coming from exactly some reverse engineers that knew how to do that and also how to do more things on these devices. And if you are in a business, that actually you should not also only protect your product, but also the data that this product will process. So actually the data of your clients or customers. And this currently is not really happening a lot and not on a wide scale. So this is actually also the reason why regulation needed to do something. And I will explain what kind of regulations will apply to the European market and to everybody that wants to sell their products here. But before I do that, I would like to quickly introduce what Swissbit is doing, what's our business, and where do we normally come from, and then also dive more into the security-related things where I'm the product manager for. So Swissbit, we come from industrial flash solutions. So in any kind of form factor, so SSDs, eMMCs, SDs, even compact flash cards, and also the newer versions of them, CFast cards, USB, or also FIDO, which is not really flash related at all. And what's so special about these things? So first, so you see this orange thing here. This is pseudo SLC flash. So it is industrial grade in terms of endurance, so lifetime, as well as temperature, and so on. So it has a lot of benefits, and it's made mainly because of internal redundancy. So you have like 3 times the amount of flash inside of one of our cards, for example. But we also have one very big difference to other competitors. We have our own flash controller. So this is and was from the company Hyperstone and is now part of Swissbit, so the whole company. And we have an own flash controller that is the interface between the host systems and the flash. And inside of this chip, we have some special hardware features like AES encryption built in hardware, as well as we can also change the firmware. So actually our products can behave different than whatever other products you might think of. So for example, our micro SD card could prevent giving you access to just read everything that's written on it. And another specialty that we can do, so in our factory in Berlin, we can also integrate different other chips into one single package. So you can really think of, okay, we already do some like flash dies, putting them on one PCB as well as a controller, but we can also add some mesh smart cards as well as complete system on chips. So we can do all these things, and this is made in Germany. So this is what Swissbit can do. And because of our toolbox, I would say, so that we have the flash controller and everything in our hands, we could do a lot of interesting solutions for different industries. For example, for drones and body cams, actually these drones or body cams, they don't really need to know that they have a different or special micro SD card inserted. It's just one of our camera cards, for example, and this cards will record everything that the drone is storing. But as soon as you pull out the card, this is recognized, and the next power cycle, you will not be able to see anything that's making sense. Everything is already encrypted with AES. And only the one that has this AES session keys can get the data back from it. Yeah. Or one also very interesting thing is for point of sale systems. Here we put or actually the point of sale system itself, it puts the receipt to the storage. Our flash controller sees, hey, there's a new receipt. It's creating a hash of it. It's taking also the last hash of the last receipt, and then it's doing a digital signature also based on the timestamp or at least some counters, so replay protection. And this thing, so this like crypto chain, is then also stored in an area where you can just read from the flash, but not write actually to. Yeah? So it's different ways of fraud protection here and integrity protection and tamper protection. And yeah, so this is where we come from, and I will also show you one special solution that we have for embedded systems later. But now also coming to one big trigger that is making security enforcing a need for more security in the EU. So there are actually two regulations. One is called Radio Equipment Directive. In Germany, it's also a Funkanlagenrichtlinie. And so normally this was about all the devices that have radio communication with the outside. And there it's mainly like electromagnetic, that you do not harm other machines that are in your electromagnetic spectrum. And also that you will not be harmed by any other devices also sending in that areas. But now, or actually so coming next year in August, you will also need to protect the network where you are maybe connected to. If you have privacy related data and somehow use it, then you have to also protect that. And if you have like monetary values storing metering data or actually currency data, then also you need to have a fraud protection. And this is targeted on all internet connected radio equipment. So actually anything that has somewhere a radio and also an IP-based communication interface. It does not need to be the same interface. So if you have a cable-based Ethernet port and also you have like an 800 megahertz garage door opener, for example, then this garage radio interface would not communicate via IP, but still it would be internet connectable because it has this Ethernet port. Yeah, as I said before, so currently everybody is, or the deadline for this would be August next year. And I will also tell some more sense, like how can you comply to this. The other thing that is coming up, and it's a bigger thing because also the focus is much wider. So first, like what products it's applicable to. So it's actually nearly all products. So products with digital elements, so everything where storage is inside or maybe an LED or whatever would be a digital product or having digital elements. And here it's not that you have to fulfill some cybersecurity requirements at the end, but you have to also consider the cybersecurity throughout the whole life cycle, from planning until the maintenance phase. So vulnerability management and so on, all these things, security by design, privacy by design, everything needs to be implemented and also well documented. This is not like you have to do this and that. So it's a risk-based cybersecurity. Yeah, so you need to do risk assessments, and based on that, you derive your methods that you would need to do. But also you need to have a vulnerability management, and also you will be obliged to only put devices into the market that are free from vulnerabilities, which is not really easy to do. So yeah, and the good thing is that this takes some more time. So currently, everybody is thinking that this will be, let me see here, oops, too much. So that this will be coming into force by, I would say in the next 3 months, somehow around then. There are also 2 versions of the act publicly available and also already agreed with the parliament. But now it needs to be signed. After the signing, I think there are several weeks until it's officially announced, and then there's a 36-month application period, after which all products that are brought to the European market need to fulfill this regulation, or need to comply with it. But what do you need to do to comply with that? So actually, normally you would see, okay, what is the harmonized standard nominated by the EU that I can follow? Big issue here is that neither for RED nor for Cyber Resilience Act that this standard is existing yet. For the RED, there is the draft standard EN 18031, parts 1 to 3. So 1 is network, 2 privacy, 3 fraud. So this 303 is a typo here, unfortunately. But this is not, so it was just refused to be nominated as the harmonized standard. So this is just, I think, 1 month ago. So currently, everybody that needs to or wants to bring new products to the market, they need to go to a notified body like TÜV, and then somebody saying, hey, this level of security is okay, and then you actually fulfill this. So this is a big struggle at the moment, and also one reason why you should really take this topic serious, because to my knowledge, there is nothing like a protection for already existing products. So I think only if a product is in the market for already 3 years. But if it's shorter time on the market and you want to just produce more units of this product, then you need to fulfill these regulations after the certain deadline. Just some little more details. I could talk a lot about this topic. So just, yeah, like some statements, again, like what is internet connected? So I already covered that, I think. And also going a little bit into the details of the network protection. So what would this mean? So you should protect the network in a way that you do not degrade its capabilities, that you avoid any harm, or at least what the harm that you can somehow touch somehow. And also you should not misuse network resources. So to me, actually, this means you should have something like a secure boot or integrity measure, so that maybe an attacker, or actually that your product will not become part of a botnet, and then also maybe do denial of service attacks against any other computers, for example. On the privacy, you have to protect the data so that it's not readable by anyone that should not have access to the data, or maybe having wiping mechanisms that really wipe data and that they cannot be recovered from flash. So these are actually 2 very good things that we can do very greatly in our flash controllers. And the fraud protection, so this is really more like for if you have monetary values, metering and so on, things in your products. For the Cyber Resilience Act, here, as I said before, so it's much wider, so it's more products falling into this category. Also, there are different high-level categories where you will always need to go to some notified body, but I think 80 or 90% of all products fall under easier thing where you could do self-declaration for CE compliance, but for this you would need to have the standard, which is not existing yet. And yeah, so maybe going to the main objective. So why is the EU forcing manufacturers to do this? So actually, it has a lot of good objectives. So you want to have fewer vulnerabilities. I think this helps everybody. Yeah. So normally an attack to an IT infrastructure is not going through one door, and that's the only vulnerability of this whatever company or asset that you want to that you target, or that an attacker is targeting. But it's a chain of smaller vulnerabilities, and one could be very cheap Wi-Fi smart home switch that is built into the, maybe it's, controlling the coffee machine of a company, and then actually through this thing you can attack the network of that company. Also, harmonization is desired, so that every player in the market will follow somehow the same rules. Currently, I think everybody could do security, but it's costly. And if nobody is doing that, and if also the customers do not really want to especially pay for security, then actually nobody will do it. Because if you would do it with your products, you would be more expensive, and maybe you would not be having the most competitive product at the end. Also, it's mainly essential cybersecurity. It's best practices that you should do. It's not like completely over-engineered, at least not from what I've seen. So it's all reasonable. And one important thing is also the transparency. So you will see in the future some labels which tell this product has cybersecurity or software updates for at least 5 years or 10 years and so on. And then maybe you can compare. So maybe you have a cheaper product that only guarantees you 2 years, but you have another one that guarantees 7 years. And if you think of like old smartphones with Android and so on laying around somewhere, actually, so I have at least some of them in the drawer, but I'm not sure, or actually I know that they will not be supported by cybersecurity updates or software updates. So what to do with them? So yeah, maybe if you have a clearer transparency of what you can do here, or maybe a longer lifetime through this regulation, this would be really great. Yeah, and also, so the manufacturer needs to do a lot of things. So also they will need to report vulnerabilities. So if you have encountered vulnerabilities or attacks on your products, you will need to share this information. Also normally in an anonymized way, so you don't need to blame yourself, but you should tell the others, hey, this is a current threat we've seen in the field, so maybe you should also have a look. You need to do documentation, you need to do software updates to patch out all the vulnerabilities, and not forget the robustness of your patch mechanism, as we also have seen last Friday, actually after our first webinar. So what can we do against this? And so we have taken the Raspberry Pi as one example device. The Raspberry Pi, I hope that most people know it. It is a small single board computer, and its only storage normally is a micro SD card. So everything it is knowing and storing is on this card. And it's actually so if you use this in an industrial project and don't do any additional measures, then it's really not secure, and also your data on this device. But what would be secure? I've said there's no harmonized standard nominated for these two regulations yet, but still there are some good standards for cybersecurity. And this one, this EN 303645, is a free standard. You can download it just now. You see the link, but you can also find it later. It's free of charge. You can read it, and it's more targeting on consumers, but it's also very usable for non-consumer use cases. And these are just the high-level captures of the chapters in it. So no universal default passwords, so no admin, and so on anymore. Yeah. So this is something that you as a company need to manage in your production. So every device needs to be provisioned individually with individual passwords. You need to have kind of information sticker or whatever for your customers and so on. This is something where we also can do stuff in our production to deliver you with these stickers or an API that will tell you which credentials were used in which flash chip, for example. Keeping software up to date, securely store sensitive parameters so that there's actually restricted access to it, secure communication, meaning secure cryptographic protocols, but also storing the keys for them securely on the platform. Minimizing the attack surface mainly also means, so like Tim said before, so if you can just dump the flash, then this is the first thing how reverse engineering can happen. If you somehow prohibit that the flash can be read out, and there are also in normal chips, there are methods for that, but also for eMMCs and micro SD cards, we have the same things, but yeah, with another mechanism like our flash controller that can protect the data there. Software integrity and so on, so that some things cannot be changed. Tim also showed that, changing not to an equal. Also, these things should be visible if somebody changed it, and then actually the system should not boot anymore. So this would also be an integrity mechanism. Also, like called secure boot. Personal data is also important to handle. And also one thing is like deleting data, for example, mainly in the consumer area. So if you pass over a device to somebody else, then you want to make sure that your data is really wiped from that device. And also maintenance and installation should be also easy. Let me now give you some example of how a Raspberry Pi could be attacked, or actually I tried to do it a different way. So how would you be as a white hat? Like, what could you do? Yeah? So actually I want to make a backup for my benefit, so that I can maybe create a duplication of this Raspberry Pi. What can I do? So actually, first of all, to understand a little bit like what is where on a embedded Linux device or on any Linux device, there's certain folders that are more interesting, certain folders that are less interesting. For example, the bin folder, it's just binaries normally, but there are some folders like etc, data, or the home directories, which may store very interesting and sensitive information, and I want to dump them. And I cannot show here, but I've created a small script that's just waiting for a card to be entered into a computer, and then it's dumping all this stuff, and then it's counting how many seconds or milliseconds it took, and then you're good and you have your copy. How this works? So actually, you just need to go to the blue one is the computer that I want to dump or create a copy of. I remove the card, I put this card to a USB card reader to maybe another Raspberry Pi. I run my script, and then I have the clone image or the data, what I need to do or want to have. I insert back the card and boot up the original system, and that's it. So actually nobody would really see that this system might be compromised now. So it would be up and running in less than a minute. But I could also, for example, talk to the back end of this device, because all the information, VPN data, AWS credentials, or whatever, all must be stored on this micro SD card. So if this device is talking to somebody, and I would have all these things now. So I could also talk to the backend system. So this is actually the potential of these kinds of easy cloning attacks. And so the vulnerability behind all these things is, or the weakness is, yeah, all data on the normal micro SD card is always readable and always changeable. And nobody is doing anything to see, is it changed? And then I will not boot anymore. So this is not happening on normal Raspberry Pi solutions. To the attack feasibility, so what do I need to do to perform this attack? So actually the experience level is very easy. The only thing that's green here, so this means green is bad for the attacker, good for the protector. The attack vector is physical. So you need to be physically, locally on your device and plug out the card. That's the only thing that helps here. But all the rest is very easy, very cheap. No special skills needed. And the damage scenarios could be many. So it could be license fraud, metering fraud, privacy violations. Maybe somebody just adds a binary to be part of a botnet. And also talking about safety things. So if this thing would store control some safety mechanism, then actually because of the lack in security and integrity, you cannot guarantee the safety anymore. So it's not part of your maybe the safety case. That also security might be a problem here, not just errors on your components or your input data. Credentials can be stolen or multiplied or given to an underground forum, and then actually everybody would have your backend password. So you need to shut down that interface, and maybe this will cause problems to your other existing devices and so on. So there are a lot of things that you can do. You just need to be a little bit creative. So just a brief explanation of what we can do here, what we can help. So in the bottom, you see this would be kind of any embedded device. So we use the Raspberry Pi just for example, but this is just, could be anything. And we can also do this for other devices and platforms. But you have apps, configs, and so on down here. And the attackers, they have different attack vectors, so physical local attacks or maybe remote attacks. Remote attacks would be maybe anything with a Wi-Fi network or as well coming from the internet. So, and they might want to steal or compromise whatever your system. And normally you would do monitoring or physical protection. So you put this system in a housing, in a room with a big lock, with the camera. And for these remote attacks, you would, for example, do software hardening, you would do attack surface reduction, setting good passwords, and so on. But on the physical level, you cannot do much. And also this is not very easy to do in certain situations. You cannot put a lock on anything. And this is especially on the left side where we have some extra protection, so that we have this hardware-based access control inside of the flash card and only show the data to authorized functions or authorized systems, as well as we do data encryption inside of the system and protect privacy and so on, and the integrity of the system. We also have this card here with an integrated HSM or secure element, so something like a TPM internally, and this really is a private key storage that you can very well use for AWS and so on, Azure, all your cloud services. And then even remote attackers would be able to use this if they would attack your system properly. So if they would gain root access, but still then they would not be able to copy this key. And this is the main protection offering that these kinds of hardware security modules bring to you. So this could also be put into one device. So how does this whole thing work? So actually we have our, one second. We have our flash controller, like I said before, and this has an access control mechanism. So this access control can be configured on a partition basis. You can say for each partition whether it should be publicly visible or privately, so only after an authentication. And you can say whether it should be read-only or read-write, or working as a CD-ROM drive, so completely read-only, or flexible read-only. So it would be normally read-only, but after an unlocking, you would be able to also write on this drive. And there are different access channels to it. So one would be for the device itself, and there are certain interfaces that actually are not very complicated, I would say. So there's some minor thing that you need to integrate. There's administrative access where you configure this whole logic, and all other access that is not authenticated should be blocked by design. So how would this work in the Raspberry Pi scenario? So here you have the standard boot flow. Yeah, so standard, you have a micro SD card that shows you all the partitions right from the beginning. You can boot through, and then you have a system that is booted, but maybe it was tampered before. So actually, you're not really sure if it's still protected or not. So how can we do something against this? So we have this special micro SD card with its access control mechanism. And if you power this micro SD card, you will only see the boot partition in read-only mode. So you will not be able to change anything there, but you will be able to read from that. And this is what the Raspberry Pi in this case needs, because it needs to boot something. And what it boots is a Swissbit adapted U-boot. So it's the open source U-boot for the Raspberry Pi with some small extra functions that will talk to our card and will tell the card, for example, the PIN that the user should enter, or it will give the system some unique data from the system where you can somehow do a fingerprinting of the system so that the unlocking is happening more or less automatically in the background. So the system does not wait for some user to enter something, but it will just work headless. And through this, we have first an immutable bootloader because of this read-only mode. We have this partition unlocking and cloning and read-out protection with our access control. And at the end, we secured the integrity of the system. The next step I will, due to the time, not be able to explain in detail. There will be some more webinars on these topics for sure. So key facts. So this new security level 2 micro SD cards that we have. So already we have some, hope you can see it. So we have some samples already. They will be soon also in the market, available at Mauser, DigiKey, Parnell, and Amazon. And you can play around with this and try out our examples for the Raspberry Pi. They have everything that I just showed. So this industrial memory, it's easy to use. This tooling is also included. And you can use this for copy and cloning protection to secure your integrity of the system. And also, if you want to externally store data on these cards, you can also do that with any kinds of embedded Linux system, as well as we also have license protection of Vibu in our card. So you can bind this card to a Vibu license and use it as a hardware anchor. So that's my part. I think I did take a little bit longer than I wanted to, but I hope it was still very interesting. To me, I thought that also the part of Tim was very, very interesting and giving at least the glimpse of how everything is working. I think it's a kind of much deeper topic than you told us before. Or Tim?
Yeah, absolutely, absolutely. So I have a question. Let's say I find this card interesting. Where could I get it? Is there any way where I could download it or order it right now? Or how should I set it up? So can you explain a bit more about that?
Yeah, so actually this card was derived from an industrial solution that we have, and now it's available like more for everybody. So it will be also available on Amazon. This might take some weeks, but you can get some samples already now, and also you could buy this industrial version. So just contact sales@swissbit.com or me directly via my email address. You can see it here, or via LinkedIn, and then we can give you some samples and also all the documentation that you need.
All right, awesome, thank you.
Okay, and also I had some questions for you. So also a colleague of mine, he asked me to tell you this question. So if you have a software development life cycle, so somebody is coding stuff, then maybe it's tested, you have CI/CD and so on. Where and then also it's deployed at the end somewhere on a hardware. Yeah. So where in this chain is your solution integrated? So is it in the IDE of the developer, or at the end, or in the production, or maybe at multiple places? Can you tell something about that?
So yeah, sure. So yeah, well, if you go to our website, emproof.com, you will basically see that we have a product which is called Nyx. And Nyx is basically a binary rewriter. So we don't touch the source code, we don't touch the compiler, we don't touch anything in between. What we do is we take the final binary or the final firmware, which would be flashed onto the device, and basically post-process it. So we have a binary to binary translator, which means we basically read in the binary, analyze it, add some protections, and then spit out a hardened binary.
Okay. And can you also give some advices? So if you've seen, because I know that you did some stuff like buffer overflow problems that you could detect, and then also you would implement some measures against that. Would you also feedback this information and give to the development team so that maybe they will not build in these problems anymore, or just circumvent them already in the source code and not on the binary level?
Yeah, so basically, let me share my screen again. So basically, what we do is we have this binary rewriting solution and protect against two kinds of protections. One of them is the anti-piracy part, and the other part is what you mentioned is exploit mitigations. So basically, in terms of anti-piracy, we do code obfuscation and these things. For exploit mitigations, we basically protect against buffer overflows and all kind of memory corruption vulnerabilities, such that they cannot be exploited by attackers. And what we typically do is that we analyze which part of the code are potentially vulnerable to these attacks. And then we harden it by design. So no, we don't give really feedback like this function might be potentially vulnerable or not, but we give feedback like this performs some interesting operations. This might be a target of attacks, so we protect that, something like that.
But you would also have a look in the code where it was, because you have the unobfuscated code, and so actually
yes,
you could
exactly
to that.
Exactly. So we basically tell it on the per function level. And for those who want to play more around with, we have a great online demo, which basically allows you, for instance, to take a source code, take the one compiler, then have a look at the compiled code, and then choose an obfuscation technique and have a look at the obfuscated code. Then you can also take a look on the disassembler or on the graph level, where you will see on the left you have more complicated graph, on the right you don't get much information because it's obfuscated. You also get a lot of explanation on top of here, and for exploit mitigations we have a quite similar demo.
Okay, coming to the most important and also last question of the webinar. So what solution is superior? So, what's the best way to protect embedded devices?
Well, this is a pretty good question. So let's say if we take a look at the attack lifecycle again, we had the hardware, where we dumped the firmware from the hardware and then looked at the software. And you can apply protections on the hardware level, and you can apply protections as a software level. And let's say both of them are quite important. Both of them orthogonal to each other. So basically they add additional layers of protection. Let's say you have the possibility to protect on the hardware side by using a cryptographic key which is stored in TPM or in HSM, or if you have some secure boot or something like that. If you can use that because it's very important. If you can add some readout protections and stuff like that, do that because it's important. But this still does not always work. Sometimes they are too expensive. Sometimes they can even be bypassed, although they are existing. So, and let's say you don't have them, or let's say somebody bypasses them, then you have the firmware and it's more or less in plain text. So If you do software hardening at the same time, you have additional layers of protection. Like then the reverse engineering is still significantly harder. Nevertheless, if you do a hardware-based protection or not. So these are basically orthogonal approaches which benefit from each other. But if you can, you should do both.
And I think also like going back to the Cyber Resilience Act, it does not tell do that, do that, do that. It tells do it on a risk basis. So you should decide, do you have a risk of physical access or not? So if you don't have any physical access risks, maybe you can live without secure boot. I'm not sure. But you should do it on the risk level. And for this, you need to know like how easy or uneasy it is to attack systems and in which ways you could attack the systems and do your decision based on that. Also, I would totally agree. So I think you cannot really compare these things. Both help you, and depending on the situation, they help you more or less depending on your system. And also, like one thing that just came to my mind right now. So I know many systems are out there that already have secure boot or could do secure boot. So there are controllers inside which you just need to enable it actually, but they are still sold without secure boot because it would take some time to do this in the manufacturing line to activate it. And this costs money at the end, and nobody wants to pay for that. So and these kinds of things are also with our solution maybe a little bit easier because at the end it comes down to entering some pins, which is much easier to handle than a cryptographic AES key, and also to derive this from something else. So also the handling of security, this is one of my goals, that the handling of security is as easy as possible while still having a good protection mechanism. And with pins also you have this replay or brute force, for example, prevention by counting the amounts of attempts that somebody had. So this is the difference between AES. So there actually you have a lot of attempts, but you have a big key. For us, we have small keys pins, but you only have 10 attempts. And so there are different approaches how you can reach the same like privacy or confidentiality on an embedded device. Yeah, so I think we took still quite some time, but I enjoyed the second recording with you, Tim.
Same.
I hope everybody also enjoyed it that was watching here. Feel free to contact Tim or me, and we wish you a nice day and a secure whatever product lifetime.
Yes, thank you very much. Have a good day. Bye.
Bye.